Perfect free throw there. So he's sick.
Hello everyone, welcome to Probability and Statistics for Data Science. What you just saw was Giannis Antetokounmpo shooting a free throw in the 2021 NBA Finals. In case you don't follow basketball, Giannis Antetokounmpo is possibly the best player right now, definitely top 3 in the NBA, but he does have a weakness in his game, which is that his free throw shooting is not that great. In order to address this, he has developed this very long routine where he makes sure that he's really concentrated when he's shooting, but it takes so long that it's almost 10 seconds, which is the maximum time allowed in the NBA to shoot free throws. Because of that, when he's playing away, the fans start chanting 1, 2, 3, 4, 5 in order to throw him off and also to try to force the referees to call a violation. I was watching this during the 2021 playoffs, and I was wondering if, because of things like this, his free throw percentage at home would be significantly different to his free throw percentage away. And today, we're going to design a hypothesis test to evaluate whether that is indeed the case. Let's get to it. As we will see, the appropriate hypothesis test for this is a two-sample test. Before we begin designing the test, let's remind ourselves about how the hypothesis testing framework works. In hypothesis testing, we first come up with a certain conjecture of interest. Then we determine a null hypothesis, which is essentially a hypothesis that contradicts our conjecture. We take a devil's advocate perspective where we say, what if what the interesting conjecture that we want to investigate does not hold? Would we still be likely to see this kind of data? That's the idea. Then we design a test statistic that captures the structure in the data that we're interested in, and which should be large if the conjecture that we're interested in actually holds. We decide on a significance level alpha, and then we gather the data and compute the test statistic and the corresponding p-value. We will remind ourselves in a moment of what the p-value actually means, and then we threshold the p-value. If the p-value is below alpha, we reject the null hypothesis, which is evidence in favor of our original conjecture. So let's make things a little bit more precise. In the case of Giannis's free throws, our conjecture is that his free throw percentage is different at home and away. So this means that our null hypothesis is that the percentage is actually the same at home and away. We are going to develop a two-sample test associated to this null hypothesis. In general, two-sample tests are for data that are separated into two groups, and where our conjecture is that the two groups are actually different in some systematic way, and our null hypothesis is that the two groups actually just come from the same distribution. In this case, he shoots the same at home and away. Okay, so that's the null hypothesis for two-sample tests. The groups are just from the same distribution. Obviously, the alternative hypothesis, which contradicts the null hypothesis and therefore corresponds to our original conjecture of interest, is that the groups are from different distributions. In this case, he shoots different at home and away. All right, so I already mentioned that we would like to have a test statistic that is large if the null hypothesis does not hold, and that also captures the structure of interest in our problem. So here, we're trying to determine whether he shoots differently at home and away, and a reasonable way to capture that is just to compare the free throw percentage at home and the free throw percentage away. So we could just basically use that as our test statistic. Let's check that it would be large if the null hypothesis does not hold. So if he shoots much better at home than away, his free throw percentage at home is indeed going to be much larger than the free throw percentage away, so the test statistic will be larger. Notice, and we will come back to this point later on, that if he happens to shoot better away, then this test statistic would not capture that. We'll get back to that point. Okay, so I'm going to peek at the data, but in general, what we would do is first develop, figure out how to compute the p-value and so on, and determine the significance level, and then look at the data. But let's just peek for a moment. This is the actual data that I gathered during the finals. It's important to emphasize that in this setup that I'm talking about, I came up with my hypothesis before the finals. Okay, so before the finals, I come up with my hypothesis, I determine the null hypothesis, I determine the test statistic, and then I look at the data. And the test statistic is equal to 34 over 44 free throws made at home minus 22 over 41 free throws attempted away. So 22 made out of 41 away. This is equal to 0.236. This looks like a pretty big difference between the home and away percentage, but can we be sure that it's not just due to random fluctuations? In order to quantify to what extent that is unlikely, we have to compute the p-value associated to this. In that if the p-value is very low, then that will be evidence against the null hypothesis that he actually shoots the same home and away, and this is just due, this difference in percentage is just due to random chance. What is the p-value? The p-value is the probability of observing a larger or equal test statistic, in this case a larger or equal difference in percentage, under the null hypothesis. In this case, under the hypothesis that his free throw percentage is actually the same at home and away, his true free throw percentage. So now we're going to design the two-sample test, and we're going to choose the two-sample C test because it's a particularly simple test that will allow us to easily illustrate the main ideas. So we have this data that are going to be the free throws, and the data are separated into two groups, A and B. Okay, so home and away. And now the one-tailed test statistic, we will see in a moment why we call this a one-tailed test statistic, is basically what we said before. It's the fraction of ones. So I should have said maybe this more explicitly, but these guys are equal to 1 or 0. So the fraction of ones that we see in the first group minus the fraction of ones that we see in the second group. That's going to be our test statistic. And now we need to model the test statistic under the null hypothesis. Our null hypotheses are going to be that the data are IID, Bernoulli, because they're either 0 or 1, and they all come from the same distribution. They have the same probability of being equal to 1, no matter whether they come from A or B. Okay, so now we need to approximate the distribution of our test statistic under this null hypothesis. In order to do that, we're going to use an approximation of the binomial distribution that is inspired by the central limit theorem. So you can check the video on the central limit theorem to learn more about this, but basically we have a binomial random variable with parameters n and theta. It is well approximated when n is not super small by a Gaussian that has mean n theta and variance n theta times 1 minus theta. Now we can go back to our test statistic and see that this approximation of the binomial gives us a way of approximate this, because this is basically a sum of Bernoulli random variables with parameter theta null, so it is binomial with parameters na and theta null, okay? Because again, each of them is equal to 1 with probability theta null, and there's na of them. So we can apply our Gaussian approximation. This is going to be approximately Gaussian with mean na times theta null. Remember that theta null in our case would be the percentage of every free throw under the null hypothesis that he always has the same percentage home and away. And na would be the number of free throws at home. Okay, and the variance is na times theta null times 1 minus theta null. But here we have a 1 over na. So what do we do with that? Well, we remember that if you have a Gaussian that has a certain mean and variance and you multiply it by a certain constant, then the mean is going to be multiplied by that constant and the variance is going to be multiplied by the square of that constant. So in this case, we take our approximation and we have to multiply by 1 over na. So the mean, we're going to multiply it by 1 over na, and the variance, we're going to multiply it by 1 over na squared. So our approximation for the free throw percentage, or the average of the first group, is going to be a Gaussian with mean theta null and this variance. We can do exactly the same thing for the second group, except that here we're also multiplying by -1. The effect of this is multiplying the mean by -1. So following exactly the same reasoning, we're going to have an approximation where the average of the second group is going to be Gaussian with mean minus theta null, and the same variance, except that here we have to plug in NB, okay, because there can be a different number of free throws, and in fact there is a way than at home, and you need to account for that. Okay, but now our test statistic is actually the sum of these two terms, right? It's the sum of this guy and this guy. So now we remember that if you have two independent Gaussians with certain means and variances, the sum is Gaussian with a mean that is equal to the sum of the means and variance that is equal to the sum of the variances. Here we do have independence under the null hypothesis because we're assuming that all the free throws are independent with the same probability. So when we separate it into the two groups, you obtain two independent random variables. Okay, so this guy and this guy are going to be independent. So basically, what is the distribution of the test statistic? Remember that the mean of this guy was theta null and the mean of this guy was minus theta null. So we get a Gaussian with mean 0, and the variance is equal to the sum of the variances. So now we have managed to derive an approximate distribution for our test statistic under this null hypothesis that the free throw percentage is always the same. You might have noticed that we have kind of a little problem, which is that we don't know theta null in practice. So what can you do about that? Well, there's a couple of different options. Something that we could do is we could just use the season percentage of free throws by Antetokounmpo or his career percentage. But usually when you do a two-sample t-test, you might not have additional data. So we're going to do what would usually be done in such cases. What you do is you just group all of the data in order to estimate theta null under this null hypothesis. So here we would just take all of the attempted free throws and divide by the total number, all of the made free throws and divide by the total number of attempted free throws. And this is how we would approximate theta null. If these are Bernoulli random variables, number of ones divided by the number of Bernoulli random variables. All right, perfect. So we have our test for Antetokounmpo's free throws. This was our test statistic. And again, if we plug in the actual data observed in the 2021 finals, we get this value for the test statistic. Now, under the null hypothesis, this guy is sampled from a Gaussian, which has mean 0, and this standard deviation. And now we're going to plug in the values. As I just said, we're going to approximate theta null by the total number of free throws made divided by the total number of free throws attempted. And here we just plug in the values of the number of free throws at home and the number of free throws away. Okay, and now the question is, how likely is it that we observe this value or a larger value if we sample from a Gaussian with this mean and this standard deviation? That is the p-value. Okay, and the standard deviation is equal to 0.103. Okay, so this under our assumptions, our test statistic is equal to a standard Gaussian with mean 0 and variance 1 multiplied by its standard deviation because it has 0 mean. This is just to make it easier to compute the probability. So if we want the p-value at any t, in particular also at the observed test statistic, is the probability that this random variable is greater than that value, or equivalently that a standard Gaussian is greater than that value divided by the standard deviation. A picture is much clearer. This is the value of the test statistic that we observe, and the probability that the test statistic under the null hypothesis, which implies that it has this Gaussian distribution, is greater or equal to that value, is just 1.1%. So it's very small. Remember that I said at the beginning that our test statistic is not sensitive to the fact that he could just shoot better away because sometimes maybe he gets super motivated by the taunting fans or whatever, and then this guy would be abnormally large. The test statistic would not know. It would be negative, would be basically on this side. For situations where you do want to be sensitive to that, you might want to take the absolute value of this test statistic. And this is easy to account for. Basically, now what we're going to do is we're going to say what's the probability that you're greater than t data or smaller than minus t data. This is called a two-tailed test because you're also taking into account extreme negative values, not only extreme positive values. That would increase the p-value to be exactly double to what we had before, still small, still below 0.05, if that is our significance level. So now we can compare the p-value against our significance level. We are going to reject the null hypothesis if the p-value is below our predetermined significance level, which is often set to 0.05. This guarantees that the probability of a false positive is going to be smaller than 0.05 or whatever significance level we choose. This is not obvious, and we're going to prove it in the next video. Okay, so have some patience for that, but for now, just accept that this whole framework is actually set up so that the probability of false positives is controlled if we threshold the p-value using this predetermined significance level. In our case, the p-value, whether we use the one-tailed or two-tailed test, is below 0.05. So we reject the null hypothesis. It's pretty clear that Antetokounmpo was shooting better at home than away. That's very clear from the data, because under the assumption that he's shooting the same, this would be extremely, extremely unlikely. And again, I set up this hypothesis before actually watching the finals, so I'm not cherry picking here. But does this actually mean that it's because of the fans like yelling out that he has a worse percentage? It actually does not. We have to be very careful about causal interpretations of such results. Here, statistical significance just tells us that it's unlikely that he's shooting the same home and away, not why. We're going to discuss the connections between hypothesis and causal inference in a future video, but basically here we don't have any randomization, so there could be confounding factors that explain why, that are the actual cause of why there is this difference between the percentages. For example, he might be more tired when he's away. He might miss his cat. There might be a lot of confounding factors that are different from the fans taunting him, which might explain the difference in percentages. Giving you a little sneak preview, in order to ensure that you can have a causal interpretation, we would need the treatment, in this case, whether he's shooting away or at home, to be independent from the potential outcome. We'll explain that more in the video, and the only way you can ensure that is to basically randomize. Here you cannot randomize because we cannot ask him to ask the fans to taunt him or not in each free throw, right? Imagine doing that in the Phoenix Suns Stadium. So we just have to live with this observational data. But again, we'll talk much more about this when we explain the connections between hypothesis testing and causal inference in a future video. And that's all I got. What have we learned? We have learned how to design and interpret a two-sample test, in this case, to determine that Antetokounmpo definitely shot better at home than away, and this was not just due to random chance in the 2021 finals. Thank you very much.